Hi, my name is Michael Henderson. I am a senior biochemistry molecular biology student.
Hi, my name is Patrick. I'm a senior biology student here at Carroll College, and this is our presentation.
Today, Patrick and I will be presenting on scientific experiments focused on antibiotic resistance, in-house novel antibiotic synthesis, and in-house screening for compounds is possible at Carroll College.
Antibiotic resistance is a growing problem within the U.S. and the world as a whole, and nearly 35,000 people die yearly from antibiotic-resistant bacteria. And this is an increasing problem within the pharmaceutical drug industry, as current-day antibiotics are growing increasingly ineffective, and new-age antibiotics are very expensive and hard to make, as they must not only treat the bacterial infection, but also circumvent antibacterial defenses. And so one such bacteria of concern is methicillin-resistant Staphylococcus aureus, otherwise known as MRSA, which is a common skin strain bacteria that can spread easily from touch to touch, especially within hospital settings.
So as Patrick had alluded to, MRSA is a bacterial species that is most commonly found on the skin of 1 in 30 people, being mostly harmless, although there are strains of MRSA that have conferred antibiotic resistance as it carries the MECA-A gene. This gene encodes P2A protein, which is a penicillin binding protein 2A. This protein is essential for formation of bacterial cell walls and has a lower affinity for beta-lactam type antibiotics. Penicillin-like antibiotics are within this class, and unfortunately, the low affinity prevents binding of these antibiotics that inhibit cell wall synthesis. For recent studies, a team of researchers used computer-generated structural relationship analysis to configure novel structures of non-beta-lactam antibiotics. All compounds were not fully synthesized, though. All of these compound possibilities. At our undergraduate institution, we aim to further synthesize these antibiotics and their derivatives to be then compared for antibiotic properties using microbiological assays.
Our hypothesis then was that some of our synthesized or any of our synthesized undergraduate oxadiazole class antibiotics would show similarities to control antibiotics, and in addition to control antibiotics, would exhibit significant drops in treated bacteria, according to bacterial growth terms.
So, for our strategy, seen here, we aim to synthesize a series of derivatized oxadiazoles, indicated by the purple circles here, meaning the R groups from the starting material would differ from its position on the ring to differing the actual substituent that was present on the ring. This is important as derivatized oxadiazoles may present a stronger binding affinity in preventing bacterial cell wall biosynthesis. Seen on the left panel schema, we have 4 primary meta-substituted R group targets that were aimed to be synthesized. Upon synthesis, we would then perform a Kirby-Bauer disc diffusion test, and then next a MIC assay, which Patrick will discuss in later in the presentation. For the antibiotic synthesis, it can be broken into 3 primary steps that we'll work on. The benzamidine compound, labeled 2, the benzoyl chloride compound, labeled 8, were both synthetic intermediates for one of the planned oxadiazoles. The schema to the right of the slide outlines a proposed reaction that was both attempted, but the compounds were currently not fully synthesized. As previously mentioned, compound 2 and 8 are intermediates for oxadiazole 3, or the siloxy-oxadiazole compound, siloxy-protecting oxadiazole compound. Ongoing synthesis is happening, but I'll present primarily today on the successful synthesis and spectral analysis attained thus far. Seen in the next slide here, for the benzamidine NMR, for the synthesis of benzamidine, which is a key intermediate for later oxadiazoles, NMR and IR spectra will obtain. Very briefly, an NMR, you might ask, is a nuclear magnetic resonance. It is an instrument that when samples which contain specific molecules are placed in a strong magnetic field, their nuclei behave like small magnets. And using a set frequency applied, we can observe the molecules' own specific frequencies in relation to neighboring nuclei, similar to a tuning fork in a guitar. And before we go into the spectral analysis, for the IR, or infrared spectroscopy, this instrument uses a infrared radiation to excite the sample's molecules, as energy is absorbed by the sample molecules and vibrates on a basis of absorption of light. So seen here is an NMR spectra. We have a diphenyl ether moiety, representative of the hydrogen atoms on the rings of the structure seen. In our circumstances, to definitively defend, we have had obtained benzamidine, and IR was necessary to be further analyzed. Seen here, from left to right, is the IR. Of these three signals, from left to right on this, were the respective functional groups. So starting on the left, two of these symmetric and asymmetric stretching of the NH2. The asymmetric stretching is normally higher in energy and seen on the left at 3,337, whereas a symmetric stretching, where the two hydrogens vibrate conservatively toward one another, is a lower energy, appearing at 3139. And furthermore, the OH stretch is also an indicative sign of being present at 3194. With these signals, and additionally with the C-double-bond-N stretch at 1677, we could conclusively show that we had isolated this functional group. And seen in the next slide here, for the benzoyl chloride NMR, for this reaction, completion was specifically verified via TLC. For this NMR, the terbutyl and the dimethyl do appear to be presently represented by the purple circle highlighted at 1 ppm and the red circle at 0.388 ppm, respectively. Additionally, the signals of HB and HA on the ring by the gold and gray circles were consistently reported with NMR data. Although further analysis is required for this NMR and our compound, as the integration patterns do appear to have displayed signs of impurities. So given that the oxadiazoles are still being synthesized and we were unable to fully characterize at this time, tests of the antibiotic properties of novel meta and para-substituted compounds were unable to be possible. Although we were able to establish controls and optimize gold standard antibiotic characterization assays to be performed at Carroll College, which Patrick will highlight next.
Yeah, so our first gold standard assay that we wanted standardized was the Kirby-Bauer. To do this, we selected 3 microbial species, Escherichia-coli, Staphylococcus aureus, and Pseudomonas aeruginosa. These were treated with 3 different control antibiotics, Gentamicin, Penicillin, and Vancomycin. On the left here, you can see an example where a plate was seeded with Staphylococcus aureus, and the control antibiotics were placed on it in disc formation. And so in this case, you can see penicillin in the bottom corner, gentamicin in the top right, and vancomycin in the top left. Then zone of inhibition was measured in millimeters, using the entire diameter of the circle, also represented in the bottom right figure. Using this zone of inhibition, we were able to calculate average zone of inhibition for each antibiotic in correlation to each of the microbial species, which we have represented here. To further analyze and give us more computational data, a MIC assay was performed. So the Kirby-Bauer gives us an indication to the sensitivity of a microbial species to an antibiotic, but this allows us to state at which point a certain concentration of antibiotic is effective against a microbial species. And so using a 12-well plate, we start off with 2,048 micrograms per milliliter of concentration and did half dilutions across all the way to plate 11 with 0 concentration in plate 12 of antibiotic. These were then seeded with a microbial species and incubated for 24 hours. As you can see, after 24 hours, there's clear visual analysis where certain wells have a higher turbidity due to microbial growth. This was computationally analyzed using a spectrophotometer, and the results are here on the right. You can see that the much more turbid wells have a much higher intensity absorbance value up here, and we begin to see some drop off at some point and then complete drop off to the baseline level of the solution. It is at this point, in this case for this species of E. coli treated with vancomycin, the drop off point was at well 4, and that correlates to a specific concentration of antibiotic. So in total, our Kirby-Bauer showed that E. coli was resistant to vancomycin and penicillin, sensitive to gentamicin. Pseudomonas aeruginosa was resistant to vancomycin and penicillin and sensitive to gentamicin, and Staphylococcus aureus had an intermediate resistance to vancomycin and a sensitivity to penicillin and gentamicin. And as you can see on the table on the right, using our minimum inhibitory concentration, there's a clear comparison between, say, the sensitivity of gentamicin and E. coli to the very low dosage needed to treat that microbial species versus, say, the dosage needed to treat it with vancomycin or penicillin. So these are our results, and they compute with known data values found throughout literature, indicating that we have created a good standardization using materials here at Carroll. So in summary, I'll let my partner take over that.
Thanks, Patrick. So yeah, as Patrick had alluded to, in summary, pathogenic species of MRSA have developed resistance to current antibiotics. And for our proposed data, we had hypothesized that meta-substituted on a diphenyl ether oxadiazole was not realized, but may possess higher antibiotic property than para-substituted R group for the oxadiazole compounds. But what we were able to achieve and present today was a gold standardization and optimization of microbiological assays to further and future be performed at Carroll College.
In conclusion, there's plenty of room for ongoing novel oxadiazole synthesis. Only 1 or 2 possible metasubstituents, or 4 of them, were pursued in our experiment, and they were not fully realized. And there's plenty of other possible substituents that could conclude further antibiotic properties. And so we hope that ongoing undergraduate students find interest in this, and in coordination with the chemistry department decide to take up this challenge and pursue these. In addition, we've also shown that we have created and standardized here at Carroll College, using the tools available to us, an effective screening method not only for control antibiotics but for any future synthesized metaphenyl or paraphenyl substituent oxadiazoles.
And to wrap up, we'd like to first acknowledge and thank Dr. Pitt for his initiative and continued guidance in these pursuing these synthetic oxadiazoles and derivatizing proposed schema.
We'd also like to thank Dr. McHugh for providing her expertise on how to standardize these techniques along with the tools necessary to perform the MIC and Kirby-Bauer assays.
And all in all, this project would not have been possible without the faculty and the facility support at Carroll College, and we would like to thank them for making this possible. And with that, thank you so much for attending our presentation today, and we'd be happy to answer any questions via email if anyone feels the need to reach out. Thank you again.